Today we're doing another induction proof from Rosen, Discrete Mathematics and its Application, Chapter 5.1, Question 8. This one's asking us to prove that 2 minus 2 times 7 plus 2 times 7 squared minus ... plus 2 times negative 7 to the n is equal to 1 minus negative 7 to the n plus 1 divided by 4. Notice that these are alternating signs, positive, negative, positive, negative. Hence, the negative 7 to the n will turn from positive to negative depending on if n is even or odd. So like always with induction, we want to start with a base case. And here, n is going to equal to 0. We are starting with 0 here. N is a non-negative integer. So we are checking that the left-hand side and the right-hand side are the same when we substitute n equals 0. So first term is 2, so we can just think of the left-hand side as being 2. Or we have this 2 minus 7 to the n, which determines each of the terms. And we can just look at negative 7 raised to 0. And anything raised to 0 is 1, so this is 2. So you can look at it as first term, or you could look at the sort of formula in the left-hand side summation. Now we're going to look at the right-hand side and see what that equals. So we have 1 minus negative 7 to the n plus 1 divided by 4. So that is going to be 1 minus 7, 0 plus 1 divided by 4. So negative 7 to the 1 is just negative 7, and then 1 minus 7 is 1 plus 7 divided by 4, or 8 divided by 4, which is 2. So the base case hold because 2 equals 2. So the right-hand side and left-hand side are the same. I don't know why I reversed those. So check. All right, so base case holds. You can check it for n equals 1 if you wanted to, just to make sure. You'll find that it's true. So now we're going to state the inductive step. So let's write down that reminder. And here we're going to assume that, and we're going to take the original statement, left-hand side and right-hand side. We have alternating signs, so this has to be negative, ... plus 2 times 7 to the negative 7 to the n. Let me write that better so we don't get lost in it. On my eraser here. So 2 times negative 7 to the n. And I want to replace n with k here, just so we'd be consistent with most classes teach replacing that variable. And then we have k plus 1 divided by 4. So we're assuming that this is true for some value of k greater than or equal to 0. Meaning if k is 10, this is true from 0 to 10. Whatever k value we choose, we're going to assume that true. And what we're going to show, we want to show that the k plus 1 case is true. Meaning that no matter what k we pick, if we prove that the next k is true, that the statement's true. And this is sort of the heart of induction. Now, this is what we call the induction hypothesis, the thing that we assume true. And we are, I'll put a little IH here just so we remember. We always use the induction hypothesis in the induction proof. That's why we established it. So when we show that the k plus 1 case is true, we're going to show that using the induction hypothesis. So again, we want to show that the k plus 1 case is true. So what we're going to do is add a term to the left-hand side. In other words, we have up to k, and we want to show that the k plus 1 term on the left is equal to the right-hand side with the next term, or k plus 1. It's going to look like this. So we'll just write it. And I keep writing positives, but this should be negative. So negative dot 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 plus, and this was 2 times negative 7 to the k. And now I'm adding a term. And again, I'm taking, I'll leave it positive because, let me write it this way. So this is the left-hand side. I'm not alternating the sign simply because I have a negative 7 here. So that sign is going to be determined by whether or not k, or k plus 1, is odd or even. If k is odd, then we have negative 2 times 7 to the k, right? Even, we would have negative 7 would turn positive. So that's why these plus plus remain plus plus. We want to show, I'm going to put a question mark above the equal sign because we don't assume it's equal. We want to show that 1 minus negative 7. Now we had k plus 1 in our induction hypothesis. So we're replacing k with k plus 1. So the right-hand side looks like k plus 1 divided by 4. If we clean that up a little bit, it's going to be 1 minus negative 7 k plus 2, all divided by 4. So again, we want to show the left-hand side equals the right-hand side. We can do that by starting with either side. In this Rosen book, and in most induction proofs where equalities and sums, I start with the sum side. In other words, the left-hand side here is the sum side. So I'm just going to write down our left-hand side. And we have this negative plus 2 times 7 to the k plus 2 times this negative 7 to the k plus 1. So that's the left-hand side, just rewritten. Now what we're going to do is I'm going to group the first k terms together. So this will be equal to 2 minus 2 times 7 plus 2 times negative 7 squared, which will just be positive, plus, I don't want to do that, minus plus dot 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 plus, my fault, negative 7 to the k. And I'm grouping all that and leaving this term here outside, because this grouping is what I assume true. That's the induction hypothesis. Remember, up here, we stated the induction hypothesis is true up until the k. And we said that this left-hand side is equal to 1 minus 7 k plus 1 divided by 4. So I can simply replace the summation by that term, because that's what it's equal to by assumption. So let's write that. This is equal to 1 minus negative 7 k plus 1 divided by 4. And I'm going to add it to this extra term, or the k plus 1 term. So this is my induction hypothesis. IH. This is where we use the induction hypothesis. All right, so now algebraically, if I can manipulate what we have here and make it look like the right-hand side, then we have shown that this statement's true by induction. Okay, so like a couple of the proofs I've done, I just want to add these first. And to add them, I need a like term on the second term here. And I'm going to write it again. And notice that if I have a 4 here, I have to multiply the top and bottom by 4. So 2 times 4 is 8. That's negative 7k plus 1. And then essentially what we have here is a summation, or sorry, a sum. Write it, plus 8, negative 7k plus 1, all divided by 4. So with that like term, top common denominator 4, this is what we have. Okay, so what we got now is 1 minus negative 7 to the k plus 1 plus 8 times negative 7 to the k plus 1. So I could factor this out in this way. What if I group them by 1 minus negative 7 to the k plus 1 minus 8 to the negative 7k plus 1. Again, all over 4. So basically, I'm grouping the k plus 1, negative 7 to the k plus 1 terms, because then we could factor that out. So I'm going to leave the 1 out here. And then we have a negative 7 to the k plus 1. And when I take a negative 7k plus 1 out, I'm left with a 1. And when I take it out of this term, I'm left with an 8. So this might look a little hairy over here on the right. But really what it is, I can write it a little neater, is 1 minus negative 7 to the k plus 1 times 1 minus 8 divided by 4. Of course, 1 minus 8 is negative 7, so I get 1 minus negative 7 to the k plus 1 times negative 7 over 4. Now I can write negative 7 as negative 7 to the 1. And remember your exponent rules. If I have the same base, I add the exponents, so it's k plus 1 plus 1. Again, divided by 4. So k plus 1 plus 1 is k plus 2. So this equals 1 minus negative 7 k plus 2 divided by 4. And this is our right-hand side. This is what we wanted to show. So that is indeed equal to the right-hand side. Therefore, the left-hand side equals the right-hand side for the k plus 1 term. And we are done. We just proved the statement. All right, so it is true that, I'm going to the original statement, 2 minus 2 times 7 plus 2 times 7 squared, minus plus plus plus, or minus dot 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 plus 2 times negative 7 to the n is indeed equal to 1 minus 7 and plus 1 divided by 2. And that's it.